the first speaker of this first session. So this is Lana Mineh from the University of Bristol, and she's going to be talking about strategies for solving the Fermi-Hubbard model on near-term quantum computers. So I will just hand over to Lana, who can get going, and look forward to hearing the talk. Thank you very much.
Hi, Ashley. Thanks for the introduction. Right, I'll just get the talk up. Okay. Great. So yeah, I'm going to talk about strategies for solving the Fermi-Hubbard model on near-term quantum computers. So I'm going to start with a brief introduction to NISQ computing, the algorithm we're using, which is the variational quantum eigensolver, the problem we're trying to solve, which is the Hubbard model, and the bulk of the talk will be about applying the VQ to the Hubbard model and our simulation results. So NISQ stands for Noisy Intermediate Scale Quantum. This is characterized by a limited number of qubits, a limited gate depth before the qubits decohere, limited qubit connectivity, so you can't do any gate between any qubits you want. Noisy gates and measurements, so there's like readout error, things like that. Crucially also, there's no error correction inbuilt, so your algorithm either has to be robust to noise or you have to implement some kind of error correction yourself. So we're interested in seeing what you can do with these restrictions. So the variational quantum eigensolver is a hybrid quantum classical algorithm, so it's quite suitable for the NISQ era, because you can outsource quite a bit of the computation to the classical computer. So the aim of this algorithm is to find the ground state of a given Hamiltonian. So we do this by inputting an ANSATZ circuit. So we make a guess for the ground state. So we kind of hope this ANSATZ circuit will parameterize the ground state. We then measure the expectation with respect to the Hamiltonian. And then we pass this value into the classical computer and run a classical optimization routine, which gives us new values of theta for our ANSATZ circuit. And we kind of repeat until we minimize. And we hope that once we've converged, we've reached like the ground state or as close to the ground state as we can get. The Hubbard model is a simplified lattice model of interacting particles in a metal. This allows us to investigate how the interactions between electrons actually change the properties of the material. So we have like a big lattice, and each site on that lattice can be occupied by an up electron and a down electron. And the two types of interaction you have are this tunneling or hopping term. So electrons can jump to neighboring sites. And then there's also this this interaction term, this on-site term. And this is kind of characterized by this value U, the Coulomb potential. And this basically just penalizes two electrons being on the same site at the same time. The largest classical simulations that have been done have been for 22 sites. So in our case, this would translate to 44 qubits. So hopefully in the next couple of years, we'd be able to do something bigger than this on a quantum computer. So the first thing we need to do is map this problem, which is fermionic, to a qubit problem. To this we use the Jordan-Wigner transformation. It's one of the simplest fermion to qubit mappings. So each site is then represented by two qubits. One of the qubits keeps track of the up electron and the other keeps track of the down electron. So it's the qubit is 0 if it's unoccupied and 1 if it's occupied with an electron. The grid actually gets mapped to a line of qubits, so we have to pick an order for our sites, and I'll kind of talk about this on the next slide. So what happens when we actually do the mapping? The on-site terms become this projector onto 1-1 state, and the hopping terms become this XX plus YY on the qubits of interest, and you get Z strings between the qubits in between with respect to the Jordan-Wigner transformation. So the ordering we choose is this kind of snake ordering, which is fairly common for lattice Hamiltonians. So this one here, the first diagram, just shows what it would look like without any spin. Of course, we have both spins. So we order all the up electrons followed by all the down electrons. And this diagram just shows what it could look like on mapped to something like the Google Sycamore hardware architecture. The next thing we need is an ANSATZ. We kind of started with the Hamiltonian variational ANSATZ because it's been around for a couple of years and it's been shown to work well with the Hubbard model. So this ANSATZ is based on intuition from the quantum adiabatic theorem, which states that you can evolve from the ground state of a Hamiltonian HA to a ground state of another Hamiltonian HB by applying evolutions of this form for a small t. So in our case, we start in the ground state of the non-interacting, so U = 0 Hubbard model. We can do this, we can prepare this ground state because this model is it's quadratic Hamiltonian, so the ground state can be prepared efficiently on a quantum computer. Then instead of alternating evolutions according to the full Hamiltonian, we alternate evolutions according to commuting terms in the Hamiltonian. And these are just like the on-site terms and 2 sets of horizontal and 2 sets of vertical. So if I just go back to this slide, this is what all the different colors represent, the commuting terms. And I should also mention that these thetas don't need to be small, unlike for the quantum adiabatic theorem. They're just angles between, say, 0 and 2 pi. The number of parameters is 5 times the depth of the ANSATZ. The idea with this depth is that the higher the depth is, the larger region you parameterize and hopefully get closer and closer to the ground state. We actually generalized the Hamiltonian variational ANSATZ and came up with something called the number preserving ANSATZ. So we replaced all the hopping and the on-site terms with a more general like number preserving unitary. And we can do this because the Hamiltonian is number preserving. So where this operator comes from is the on-site and the hopping gates. So now one depth or one layer of the ANSATZ now consists of applying these unitaries across each pair of qubits that correspond to fermions that interact. And the nice thing about this ANSATZ is that because it's more general, you can either start in the U = 0 ground state like before, or you can start in a computational basis state. The number of parameters is now much bigger, but hopefully that means that as we're parameterizing more of the, hopefully we're parameterizing more of the region with a lower actual circuit depth. Yeah. Okay. So I don't have time to talk about it here, but we basically implement an efficient version of these ANSATZ using something called swap networks. And this table just kind of shows what the actual like physical circuit depth would be for one like ANSATZ, one ANSATZ layer for different architectures. So we chose 5 by 5 here because it's just beyond the realm of what can be done classically. So really, like the connectivity does have a massive difference on our circuit depth. The next thing we need to do is measure the energy. So we need to measure the expectation of every term in this Hamiltonian. And actually, a lot of these terms can be measured in parallel. And in fact, using the same kind of 5 different commuting terms as before with the Hamiltonian variational ANSATZ. So you can measure all the on-site terms with one preparation of the circuit, and then you have the 2 sets of horizontal and the 2 sets of vertical. Right, so the VQ algorithm makes a lot of calls to the quantum computer. So one circuit evaluation is one run of the quantum computer, but you need 5 runs of the computer to measure all of the terms in the Hamiltonian. And then of course you then want to do like M number of those measurements to get a good estimate. So often it would be in like the thousands. So by doing some kind of back of the envelope calculations, making some assumptions for 2-qubit gate time and circuit depth and things like that. In approximately 14 hours, you could produce 100,000 energy estimates to an accuracy of 10 to the -2. So this gives us like a good, like an upper limit, a budget of like I say function evaluations we want the optimizer to do. It's also really important that we find an optimizer that's robust to noise, statistical or otherwise. So for this reason, we tested two different optimizers. One's SPSA, which is a type of stochastic gradient descent. Another one is coordinate descent. Right, okay. So we did simulations with 3 levels of realism. The first thing we did was we simulated the exact energy measurements by cheating and looking at the wave function. And this just filters out which ANSATZ are effective. Because if it won't work in this scenario, it won't work later with more noise. The next level is we simulated the energy measurements as if they were performed on a quantum computer, but we assumed that the computer itself was perfect. And this kind of tests which optimizers are good at handling noise or statistical noise. The final level was we simulated the energy measurements and we simulated noise on top of that. And this allowed us to kind of test like error detection procedures and that kind of thing. So with the exact measurements, we tested every grid size up to 12 sites. And we tested the standard Hamiltonian variational, our swap network version of the Hamiltonian variational, and the number preserving. And so an initial test you can do is to determine how effective your ANSATZ is to find out what the depth you need to get to, what ANSATZ depth you need to do to produce the ground state to 99% fidelity. As you can see, like number preserving tends to perform better because it has way more parameters. And this graph here just kind of shows that something is happening when you add a depth, like it is getting close to the ground state every time, which is like reassuring to see. For realistic measurements, this kind of just compares coordinate descent and SPSA for a 3x3 grid. We fixed like the same number of circuit evaluations to compare the two. As you can see, like SPSA, it performs pretty well. It's kind of designed to work with noise. And even when you pass it, even when you use a very low number of measurements to estimate the energy, it still gets quite close to the ground state. Noisy VQE, we considered a simple depolarizing noise model. And the highest noise rate we examined was like 10 to the -3. We also did a couple of others. The error detection procedure we tried was a very simple one. So like I said before, the Hamiltonian and the ANSATZ are number preserving. So a simple thing you can do to check if something's gone wrong is to, once you've done the measurement, to check the Hamming weight, and if that's not the number you were expecting, then something's gone wrong, so you throw that away and do another run of the quantum computer. So SPSA doesn't see a massive improvement with this error detection, but coordinate descent does. So in conclusion, so for exact measurements, our results are kind of consistent with a grid with n sites needing order n layers. And in fact, even in the worst cases, we always found that at most 1.5 n layers were needed. For realistic measurements, we showed that SPSA and coordinate descent are both able to achieve a relatively high fidelity with the ground state, even by just making a number of measurements, which would take a couple of hours on a real quantum computer. Noisy VQE, when we simulated depolarizing noise, error rates of up to 10 to the -3 actually did not have a significant effect on the fidelity of the solution. Whether this will hold for an actual quantum computer with more complex noise remains to be seen. So it seems plausible that an instance of the Hubbard model could actually be solved, well, that's larger than what has been done classically, by just optimizing over quantum circuits with depth of a couple of hundred. Yeah. So thanks for listening. I'm just going to finish with a little plug. Phasecraft is hiring, so if you found any of this interesting, please get in touch. Yeah, are there any questions?
Great. Thank you very much, Lana, for that fantastic talk and for finishing perfectly on time. So indeed, like now is a great opportunity to ask questions. So I can see that one's already appeared in the Slack channel, but maybe just to give people a chance to ask one or two more, perhaps, and then I will go through them. I might start out with asking a question myself, if that's okay. So you mentioned on one of your slides that we are using the SPSA algorithm, and in fact a slightly modified version of SPSA where you have like rougher and smoother measurements. I was just wondering if you could say a few words more about the effect of that optimization. I mean, yeah, does it make things better? Like what's the difference from normal SPSA?
Yeah, well, actually in our paper, we've got a graph where we've compared like the two. Basically SPSA changes the kind of the step size every time. So by kind of doing like a really coarse SPSA and then starting again from that point you've got to and doing another version, another SPSA, it kind of you kind of improve your solution every time. And you don't really need like the 110,000 measurements. I mean, eventually you kind of get to the same, you kind of get to the same solution, but this kind of gets you there faster with a fewer circuit evaluations. Yeah.
Right, fantastic. Yeah. Thank you very much. Okay, so oh, wow. Okay, that's quite a lot of questions now. Okay, so there was a question at the top. I sort of roughly go through in order. For a question at the top from Tom Parks, who's asking if simulation code is going to be available.
I guess because this was worked on with Phasecraft, I'm not sure if it will become available. Yeah, I guess Ashley, you would know more about that.
Yeah, okay. I mean, but maybe it's worth saying that the data associated with this paper is already, I think, available online. Yeah, I can see it is already available online. So if people want to see all of the results that go into all of the figures that Lana's presented and many others in the paper, then that is accessible online. At the moment, though, we don't plan to release the code itself, the simulation code. Okay, I'm just going to go through the questions sort of in order here. Now, the next one is by Joel Klassen, who's asking about the effect of choosing alternative orderings of the Jordan-Wigner transformation.
Right, so the reason we kind of chose this this kind of snake ordering we have here is because you can actually do this measuring like lots of terms in parallels. It turns out you can't actually group it into these 5 commuting sets if you've got like a different ordering. So if you're just going like kind of straight down like you would kind of imagine. So yeah, the actual ordering does have a lot of effects on how you did the measurements and the actual circuit you implement. Yeah.
Cool. Thank you. And Ross Duncan's asking, how do we measure the Hamming weight and the Hamiltonian terms at the same time?
You basically, when you're doing the measurements, you kind of do, you basically do a computational basis measurement. So it boils down to just counting the number of ones you've got at the end.
Okay. So there's next a question from Joan Camps asking, what's the intuition that the application of this adiabatic time evolution results with alternate Hamiltonians works? Is there any intuition that goes into this this result that says that, you know, alternating these 2 Hamiltonian types should find us the ground state?
I mean, I would say the quantum adiabatic theorem is kind of like the intuition. It's you kind of start from something that has worked previously, and this is just kind of a different it's a different way of looking at it. You're basically like evolving according to terms in the Hamiltonian. So you're going to be doing you're going to be kind of preserving like the properties of the Hamiltonian, stuff like number preserving, maybe symmetries and that kind of thing. So yeah, I guess maybe I could talk about that more later as well. Yeah,
okay. Yeah, excellent. So I think, yeah, maybe just to make sure we don't run too late for the next talk, I'll maybe cover one or two more questions, and then indeed, if you don't mind answering questions on Slack, Lana, that would be fantastic. So, okay, just a couple more questions. So one by Gianluca Anselmetti, who's asking what platform we're using for the simulation of VQE.
So we use C++, and we actually used Quest by Simon Benjamin's group at the University of Oxford to simulate the quantum computer.
Cool. Fantastic. And there's a question, well, a related question's come up by a couple of people, but this specific one's by Barbara Terhal, who's asking about 1% error rates, so slightly higher error rates than we considered.
Yeah, I guess we didn't actually test that. I would imagine it would perform slightly worse. Yeah, it'd be interesting to see.